J'ai regardé cette conjecture de R2, c'est quelqu'un qui l'a vérifié jusqu'à 2 puissance 50 récemment.
Oh, cool. Ouais, oui. Ah, merci. C'est de la craie spéciale japonaise. For a high-level talk.
Welcome back. Professor Ramanujan will continue with his lectures. And Saurabh has some announcement. Okay, so some little bad news here. Tomorrow's trip has been cancelled. So if you still want to go to the city, you can use the shuttle, which goes from ICTS, and you can do your own touring. So he was quoting actually very high, so it got cancelled.
The bus from 2 p.m. to 10.
Okay. This is going to be the last lecture, finally, because of some plane difficulties and life. In the first half, I'm going to prove again the Brun-Titchmarsh inequality. But I'm going to do it through the Parseval identity. So what I'm going to do is that I'm going to state the final result. Then I'll rush to the heart of the proof, because now I can write the heart of the proof very simply. And then I'll talk, prof. And I'll give an element of the proof later. For the second part, I still don't know what I have an idea of what I'll do. Most probably in the second part, I'll do part of what I should have done on Friday. Okay, so the first theorem that I'm going to prove, I need a piece of paper. Ah oui. Let be non-negative. N less than n. And UN non-zero implies for every Q less than capital Q. N is prime to Q. I mean, the support is essentially the primes. That's what I'm writing. Yeah? If I did not get mistaken, I say if UN is non-zero, then N is prime to everyone which is less than Q, and this Q is like a square root of N, so it's the way you mimic the primes. Then, let me check, simplify a bit, yes. G of Q, 1 plus Q square by V, integral from minus infinity to infinity. So that's going to be the first result. You have my favorite function G of Q, the one that is larger than log Q, sum of nu square Q upon phi of Q. you have a kind of you have two parameters, a new parameter v that is here, and you control the oscillation of the function. The corollary is going to be this one. What I want to stress out is that it's amazing, but I use the fact that UN is non-negative. Usually in large sieve, you don't use, but here you need it. Same hypothesis. And you get G of Q 1 minus 2 square root 2. You don't care. 4 Q upon square root of n. Sum of UN square less than n times of UN square. This one, huh? No, it's just, so it's a positive stuff. Absolutely. It's just the sum upon the ends that are located around T at distance V. And essentially, you have an interval of length n, and V is going to be n by log n. See? So you shift just a bit. V is, I mean, if I could take V equal to n, I'll be happy. I cannot, but you just shift a bit. Yeah. And so when you optimize your V and you find a lower bound for that, what you get is this inequality. N. Any sequence that has this property. Typically primes in an interval. Huh? So, and corollary. Yes. Yes. To be, what I'll prove is that I'll prove UN times A of n minus t, a convolution of two sequences. It will depend on a function, and the function I've chosen is a characteristic function of the interval minus VV. So that's the simplest function I could think of. In fact, I'm going to prove something with a more complicated kernel here. So, of course, you know what I'm going to get. Because you take a Q to be square root n divided by log n. So it's 1 minus little of 1. This one is a log of square root of n divided by log n. So it's essentially 1/2 of log n. So you get that this number square less than 2 n upon 1/2 of log n. This one is 0 or 1, so this one is equal to that. So that is less than 2n upon log n. So we prove again the Brundtland-Marsh inequality, and we lose again a factor 2. Now I'm going to show you the proof. And the question that I've been asking myself for the last 8 months, where do I lose something? So proof. No, not proof. Okay. Step 1. Well, I'm going to tell you that the sum for Q less than capital Q, sum for A mod star Q of S, I'm forgetting something. Of the integral of A by Q minus 1 minus delta A by Q plus delta of S of alpha square d alpha is less than sum of UN square of course, I've set S of alpha, oh, I shouldn't, with S of alpha equals the sum of UN E n alpha, n less than n, and delta equal 1 upon 2 q square. I think now that you've heard the talk of Rita Brata and the talk of Keshav, you absolutely happy with that. Simply, I take a uniform length of the interval. I could take a length that depends on Q. You can do the Klosterman decomposition. Essentially, that's the Faraday dissection, okay? You don't believe you lose much. You could even have equality if you were a bit more refined here and here. But to make the talk simple, I do the simplest stuff. Step 2. I'm saying that integral from, oh, sorry. I'm saying that the sum for A, no, yes, mod star Q of S of A by Q plus beta square is larger than mu square Q upon phi of Q S of beta square. I claim that I have already proved that, in fact, because I've proved it with a sequence UN for the primes. Yeah? And instead of the sequence UM, you take UM times EM beta, and that gives you S of beta instead of S of 0. It's just a shift. Okay? Okay, I'm going to make a very long proof, so I'll put another step. Step 4. No. I wanted to get a longer proof, you know. Step 3, mu square Q upon phi of Q, integral from minus delta to delta of f of beta square d beta less than what it should be. Up minus delta of f by q plus beta square d beta. Yeah, I integrate. Then you have that. Okay, I could put a step 4, but I can shorten the. You have this one, you have this one. You put them together, yeah, and you get g of q integral from minus delta to delta of s of beta square d beta less than sum of un square. That's going to be, I mean, this one is going to act. I told you to get a large Sieve stuff, you need a local lower bound, which I have here, and a global upper bound that encompasses all your characters, which is here. When you put them together, you get this one. If I can get a lower bound of this one, that's going to be my work now. I'm home. We believe that we don't lose much here. We believe we don't lose much here. We believe that we don't lose a factor 2 here. I mean, I believe that, you know. So I was very excited and I computed many things. I'm going to lose a factor 2, okay. There's something that you, so now I'm going to talk a bit. There's something that you may see. If delta is too small, less than 1 by n, then this integral is essentially the central value times the length of the interval. by continuity, not continuity, by differentiability, I mean, it's the same value. Yeah? So most probably you cannot take q square larger than square root n. I mean, here, since you have g of q, you could say, let me take q equal n to the 2/3. Then I'll get 2/3 of log n, and I'll be happy. But philosophically, it's not normal. I mean, it shouldn't work. The second thing, yeah. Okay, so discussion. The second thing is about, as you saw before, instead of, your question, my question is to get a lower bound, S of 0 squared. That's what I would like to get. Huh? When the UN are non-negative. Why is it an interesting hypothesis? Because then this polynomial takes its maximum at 0. So you want to find a lower bound like that, but that's completely harmonic analysis. There's not much number theory left in this problem. If you well, you can expand this one, but you can also look. Okay, I'll do a. If you expand, you get the sum upon nm of un bar of sine 2 pi n minus m delta upon pi n minus m. This one. Maybe you remember what you saw in the previous talk. It was a similar thing. It's easier to look at the problem with continuous variable. So look at this problem. Fourier transform of a function in L2. This one, dt. Yes. And so this one is the sum from 0 to 1 of f of y prime sine 2 pi y minus y. Okay, I forgot a parameter somewhere. I should have delta n here. Wait. There should be delta n here. dy prime. It's because here it's delta n. And f in L2 of 0, 1. I mean, if you essentially, it's a step function, a function between un and un plus 1, you put un, and then you have a function between n and n plus 1, you put un plus 1, and you approximate like that, and you can go from a sum to a function. I don't care about the error term because it's only a discussion. Anyway, you have this kernel, and I'm going to tell you, I'm not going to tell you much, but I want to say some big words. Maybe you don't recognize things so much here, but this quantity here, so I'm going to put C equal delta n. Yes. And this quantity, f hat t dt, so it's equal to the scalar product, so sum from 0 of 1 of f of y times integral from 0 to 1 of f of y prime sine 2 pi c y minus y prime upon pi y minus y prime dy dy prime, dy. Huh? What did I? Oh, yes. Oh, yes. Absolutely. This one is an operator. Okay? That's integral operator. So most probably you're not so familiar with functional analysis, but this one is a Hilbert-Schmidt operator. So it's very well studied. It's Hilbert-Schmidt. This kernel is in fact C1 and C2, and see how much you want. So in fact, it's sort of trace class, meaning that you can define a trace for this operator. And it is compact. So it means that you have a enumerable family of eigenvalues, lambda naught, lambda 1, lambda 2, and so on, decreasing. An enumerate family of non-zero eigenvalues. You have it's also a symmetric operator, a symmetric positive operator. So you have eigenvalues 0, okay, lambda 0, lambda 1, and so on, lambda n, which depend on C, in fact. Okay. You have eigenvalues, lambda naught of C, and so on, eigenvectors that are all orthogonal because it's self-adjoint. And they are called, they have a name. Oh, sorry. Because it's Hilbert-Schmidt, you know that the sum of the lambda n square is equal to the square of your kernel. So sum 0 to 1, oh, I'm not sure. I'm not sure. You can express. It is known. I think it's the integral of from 0 to 1 of this kernel square. Yeah. It's a very simple expression, but I don't want to write. There's maybe something in front. I'm not so sure. It's of trace class, so you know that the sum of lambda n, that's the trace, the sum of the eigenvalue, that's the trace. The trace is given by the diagonal here. When y equal to y prime, it's 1, it's C, it turns out, yeah. So I should put C here, in fact. Okay. So the trace is equal to C. So since they are all positive, you know that they are all bounded by C. Okay. And they have a name. They have an ugly name. Prahlad. I mean, if you want to find them on NIST or even on Wikipedia, spheroidal wave functions. And that's all I know. That's all I know because people have been studying that. They're also called Schleppian functions. Schleppian is someone who has written a very important, very influential paper in the 70s. So people have been computing them in many things because they use them in signal processing, essentially. It's band limited stuff. We have lots of tables of them, but we have no expressions of them. Especially, we have no expression. We would like I would like the dependence in C, so that I can say C is my delta n. I would like to choose this guy. I don't have anything like that. And also now that you can, so now this you can write as a sum of lambda n times the scalar product of your function f, scalar product with psi n. All of that is positive. You're very happy. But I would like to know what is the effect on the function 1. And I don't know. This is to tell you that there's been lots of work which does not go exactly in the direction we would like. So I ask people from functional analysis whether they have any idea how to get this inequality. And what they prove, so this one is an inequality, you're trying to see whether the mass can escape a lot from your Fourier transform. No? And what they've been studying is how the mass can accumulate. What? I don't know. Maybe we can talk about it. This is this C. Yes. Yeah, because this my function depends on this parameter, and it's going to appear here. Especially since I will have C is delta n, it will tend to go to infinity. So I would like to know the dependence in the parameters, and I don't have. Yes, the trace. It's called, this one is called Lidsky's theorem of 1971. Lidsky, it depends, sometimes there's a, Lidsky's theorem tells you, so, I've learned lots of things, I've read lots of things, but it doesn't solve my problem because, so to tell you that people are studying, it's not clear what we should do. There's something else I have to say. No, so I already told you that it looked as if it were optimal. So now let us try to get a lower bound of this one in the way I put. Oh, oula. Ooh la la. Okay. First, a very simple one, very simple lemma. Is this one. Sum from minus infinity to plus infinity of sum of A times T minus M. Let's put a square, dt, is equal to, well, let A be a function. Sorry, it's not so easy to find on the blackboard. A function whose support is on minus v. And you'll assume that it's in L1 into L2. This one, so it's like the integral from minus v to, no, from minus v to n plus v, yeah, because of the support. So it's equal to sigma square upon n, 1 minus 2v by n, sum of the un square, plus integral from minus v. You'll see it's longer to write than to prove. A of t minus m minus sigma sum of the upon n square dt with sigma equal integral of minus v to v of A of t dt. What I'm writing is that this one is equal to the variance plus the square of the middle value. Okay, nothing more. I'm just comparing that with medium value, average value, which is this one, and I'm writing that this plus this. And what I'm going to say is that this one, I don't know how to handle, so this one is going to be larger than that. Okay? And if you take A to be the characteristic function between minus V and plus V, you'll go from the first theorem to the second theorem. And you optimize V. You optimize your parameter. So that's very easy once you have that to go to this part. It's unclear whether I've lost something or not. I don't know. Now, we still need to reach this part. And what we have at the beginning, this one is a lemma. I don't write the proof because it's trivial. And now I'm going to take, let A be a function. Again, it's longer to write than to understand. No, it's minus V to V of length 2V. Here I put 2V. Where? Oh, it's N. Yeah, otherwise it would have been 2V, I agree. Yes. No, it's the average of this one. The average of this one multiplied by this function. Okay, let it be a function on minus VV, which is even. A decreases when V is positive. So it's a bump function. Typically minus VV. And I tell you, and it belongs to, A belongs to L1 enter L2 of minus VV. I don't know whether it's required, but then this function, A of t, A of y minus t, dt, it is equal to this function, A of t, A of t minus y, because it is even, and it non-increasing when y increases, y positive increases. Essentially, because there are two bumps, okay? There are two little hills. Yeah. When the little hill coincide, you have maximum, and when you shift y, the hill shift one from another, and the intersection, which is what you have here, gets smaller and smaller. Okay, that's what it's saying, and in fact, it's only because the proof is clearer like that. I'm going to take A of V equal A naught of B equals the characteristic function of minus VV. Okay? So I state it in general because the proof is clearer when you have a general kernel. But in fact, you only have to prove this one in this case. And in this case, the convolution of A naught T, A naught Y minus T dt, it is equal to 2V minus Y plus. I mean, it's a 10th function. You know? Okay. Once you have that, you can remove all this discussion. Okay. This one disappeared. I need to build just one function and the proof is almost over. So I'm going to put that D of 200 parameters, but D of minus M minus D of A naught delta of I have to think, is equal to the integral from 0 to infinity of C hat D hat, C hat of minus lambda lambda delta of U, so it's going to be U, B of lambda de lambda, okay, set with sum from A of t, A of y minus t dt, assume is the sum of y to infinity of b of t dt. So in case of A naught, b of t is simply the one functions between 0 and 2v, okay? And what is this function? This one was the upper bound for the characteristic function of the interval minus lambda lambda, okay? So I'm just taking the sum of this upper bound of characteristic function. And so what can you say? You can say the Fourier transform is in U, okay? So the Fourier transform has nothing to do with the integration. So you can take the Fourier transform inside, and this one is larger than the characteristic function of an interval. Huh? So you discover that D of A delta U, t is larger than the sum from 0. So it means that, wait, I have something which is wrong. Yes, it means that U has to be less than lambda, meaning that lambda has to be larger than U. So you have U to infinity of B of lambda d lambda. Okay, you have this upper bound, and you have and you know that D hat A of delta of U, it is less than, well, you have an upper bound for this one. Remember, it was 2 lambda plus delta minus 1. Huh? So this one is bounded by what? Oh, if U is larger than delta, this Fourier transform vanishes. Okay? So D hat A delta of U equals 0 when U is larger than delta. And it is bounded above by, I don't remember what. You compute a bit and you find an upper bound, which should be L1 norm plus twice L2 norm. Delta minus 1 and delta minus 1 should be the A2 norm square, plus the A1 norm square also. Okay. Now that you have this material, it's a bit boring, I understand. You have your stuff here, you'll see it's magic. You say that it is larger than, because this one, this function divided by this one is less than the characteristic function of the interval minus delta to delta. Okay? So it's larger than 1 upon delta minus 1. For A naught, the L2 norm of A naught, which is equal to 2V. The L1 norm square of A naught is equal to 4V square, 4V square. So 2V plus 4V square times the integral of minus delta to delta of f of beta square d hat of A naught delta beta d beta. I have a characteristic function of an interval. I replace it by that. I can remove this part because the support is finite, is inside this one, plus, minus. I expand because, so this one is larger than 1 upon 4V square plus 2V delta minus 1, sum for Nm of um square. And what you get here, it's sum from minus infinity to infinity of d hat A naught delta beta E n minus m beta, or m minus n d beta. Okay? That's your function d in n minus m. And your function d in m minus m is larger than, what did I say? Is larger than, wait, that's not what I wanted. Wait. No, what I wanted is it's larger than, wait. I'm skipping a step. No, it was correct, but yes, of course. It is larger than that, that's what I proved, but this one is equal to that. Okay. A of t, A of y minus t dt. Okay? Okay, that you can forget. Okay, so this one is what is the sum for Nm of um bar, let's say, d integral from minus infinity to infinity of A naught of t, A naught of m minus n minus t dt. I was able to go from here to here because um are non-negative, and I can take a lower bound. That's why I use this property. Huh? What? Oh yes, yes. Otherwise, it wouldn't be correct. Plus delta plus 2v delta minus 1. But this one, you can put one of the n in the other part, and you recognize the square. So this one is also the integral from minus infinity to plus infinity of the sum for n of un A naught of t minus n, or n minus t if you want, square dt. Okay? There was a little part of technique in between, but look at the proof. You have this one. You take a lower bound by something which behaves nicely with respect to Fourier. This one has a Fourier transform which is non-negative, and that you can interpret as sums of squares, which is this one. You take A naught to be your favorite function between minus v and v. You also have proved the first theorem, and the second one, because this one I can relate to the average, gives you that. So that's, no, really? Yes, that's almost the end. So the question is that this proof is valid for the set of primes between square root n and n. Okay? We believe that most of what we've done here, I mean, what I have done, I'm not going to include you in my mistakes. What has been done is optimal. So somewhere there's a mistake. I mean, there's a wrong hypothesis. Somewhere for the large Qs, as far as I understand, it does not behave as we tend to believe it behaves. And that's a big question for the new generation. For the time being, the only property we're using is always the same one, sum of SA by Q square larger than mu of Q upon phi of Q S of naught square. That's the property of the primes we're using. Exceptionally, I was very happy here because I use an additional hypothesis, non-negative. So I thought maybe it's not a very deep hypothesis, but at least I'm able to use it. Okay, one word before I end. This function here, you can build it in another way. I told you to read the paper of Valeur, extremal functions in Fourier analysis. If you read the paper of Valeur and you take the upper bound of 1 minus of the 10 function, Valeur gives you an upper bound for the characteristic function of an interval, but he also gives you an upper bound for any kind of function on the real line. So take an upper bound for the 10 function, you get this function. Except that Valeur is able to handle functions that are not especially decreasing, in which case you have to replace this one with this one or that one with the absolute variation of the function. But at some point of time, I thought what was very interesting was this lemma. But okay, that's all. We stop for 5 minutes, yeah? Is that, yes? Cool, thank you. And then you'll be able to leave.
another little bit change in schedule, the Friday second half will be off. Thursday second half, but Friday second half both will be off.
First half will be Gyan Prakash and second half will be.
Yeah, on Friday, the first half will be just like the second half and second half. And then play.
Okay. I've prepared things till about 7 o'clock. So I hope you have your meal. Maybe I'll skip one of them. First, I would like to tell you, very often you from interval n and to n. What happens to interval n and to n when n is not large? This problem exists truly everywhere. So, for instance, the number of twin primes E is that P plus 2 is a prime, and B belongs to M plus n. This one we have an upper bound like some constant P2 n upon log n square. In fact, log n square minus ego of m. Okay. This constant has not been touched in the last 70 years. What has been done is that when m equals 1, we're able to diminish this constant, but in an arbitrary interval, we don't know how to do L. It has to be improved. Montgomery and Vaughan, by using the weighted large sieve, didn't tell you about it, were able to remove this one and put 1. That's Montgomery and Vaughan. That I'm not able to do the things that I'm doing. It looks like a trivial problem. I'm not able to do it, and the weighted large sieve is able to do it, so there's something more to understand it. The first remark. The second remark is that
Professor, use the mic.
sorry. I remember this. Okay. Now I cannot escape. The second thing is that I have to do a bit of advertisement for Binaja, who is here, Surya DS, who is taking care of his dog, so he's not here, and myself are here. We got upper bound for the number of norms in an interval. I don't want to state the full result, but you take an interval m plus n. M is very large, kind of exponential n. You have a number field, fixed number field of degree 23, and you look at the norms from this number field, and you want to know how many norms you find in an interval, or to have an upper bound for this part. And so we call it a Brunstich-March interval because it counts, it gives an upper bound for the number of norms in an interval. Sorry? Norms with a multiplicity. Yes. That would be even harder. No. Okay, and many people just now are doing analytic number theory with algebra.
For arbitrary number field?
Yeah, for arbitrary number field. That's not my part. There's lots of people who are doing analytic algebraic number theories these days. You can find several papers in enumerative combinatoric. Bhargava somehow, it's not that he started, but he he gave a big impulse to this movement. And now lots of people are looking at this kind of thing. I think huh? What? Yes. No, I'm just saying that analytic algebraic number theory, but essentially people who are able to use Sieve, you have to know Sieve to be able to use it. So I think there's a lot of things to do and things interesting to discover that will be good for the community. Okay, now that I've put my employment part, some easy thing. Okay, because you're tired, so I have to try to wake you up. I told you that that I was able to prove the Brun-Titchmarsh theorem several times in the interval between m and m plus n. And regularly, I skip the arithmetic progression. In fact, if you look at the method I'm using, it can be extended to arithmetic progression. But to do that, you'll have to find a lower bound for this guy, which is a sum for q less than z, q prime to k of mu square q upon phi of q. G1 is a function I've used. So I'm going to give you a very simple lemma, which is due to Van Lint and Richert in 1965. It's amazing because essentially it's only 5 lines in this paper, and 60 years later, what remains of their paper is this wonderful proof that that I'm going to give now. Because if you want to try to handle that with k of any size, it can be tricky. So here is the ID. They start from G of Z. So this one now, you know what it is. Up, it's a Q. Mu square Q upon phi of Q. And they say, let us sort them out according to the GCD with K. Q less than Z. The GCD with K is equal to D of mu square Q upon phi of Q. It's a partition. Partition according to the GCD. So I put the GCD out. Sum for D divides K of mu square K, mu square D, because only D of, you can assume that that K is a square free. Anyway, only the square free kernel of K appears. Mu of D upon phi of D. Then when you get, is let's say L less than Z by D. And because this one is square free, L is going to be prime to Q. You've removed the part of your integer, no, we're going to prime to K. You remove the part of K that has prime factors with K, of Q that has prime factor with K. What remains, so you have D that divides K, and what remains is something that is prime to it. So mu square Q, mu square L upon phi of L. Okay, and this one, you know that it's, if you want to use some notation, it is this one. G, it's K, sorry. Gk of Z by D. Okay? I've written G of Z is equal to that. I mean, what can you do with that? Well, it's very simple. So let me put it in the middle of the board. mu square d upon phi of d, gk of z by d. The g function or gk function is a non-decreasing function. In French, it's an increasing function. It's a bit simpler. So this one is larger than the smallest is d equal to k. So the sum for d divides k of mu square d upon phi of d g k of z by k. And reverse, it is less than sum for d divides k mu square d upon phi of d g k of z. Yeah? This one is equal to k. Oh, power, no, you don't see anything. It's equal to k, you don't see anything. It's equal to k upon phi of k. So what you've proved is very simply that gk of z times k upon phi of k is larger than g1j of z, which is j1, which is larger than k upon phi of k, jk of z by k, which you can invert if you want, because it's gk that you want. Jk of z is less than phi of k by k j of zk. It is larger than phi of k upon k g of z. Okay, it's a neat proof. I mean, it's wonderful. We use it constantly in Selbach-Sieve when we say that the lambda d are less than 1. Before Van Lint and Richert, we knew that the lambda d were less than d to the epsilon. Okay? Since you know that g of z is larger than log z, it gives you a lower bound, but in fact, I can show you very easily that g of z is essentially equivalent to log z. So this one is phi of k upon k times log z plus log k. Okay, so it's essentially phi of k by k log z, phi of k by k log z, and you have an asymptotic. And that's very easy. Selberg, who was okay, okay, quite good. 2. Okay. Now I'm going to go and give you a little part of my last lecture. You saw in the last proof that what was important were the large values of my trigonometric polynomial. S A by Q, we expect that it is large. We say, I mean, S alpha on the unit circle, we believe that it is large in A by Q. And so we look at this point and around this point. And we believe that it's the main contribution of this integral. I showed you a proof that tells you that maybe there's a difficulty with that. Is that true or not true? So then I started investigating what are the large values, large point of this trigonometric polynomial. So let me give a definition. Oh no. So I'm going to get a fixed trigonometric polynomial. S of alpha is equal to the sum for some primes in an interval. because that's going to simplify the case. A definition. We look at the set C of capital A. It's a set of point alpha on the unit circle, so that S of alpha is larger than S of 0 divided by capital A. No, something big. Imagine A equal to 2, or means S of alpha is very big. S is a continuous, it's not a, well, it's a continuous function. So this one is a collection of arc. It's a compact set, it's a collection of arc, and so it's a collection of arcs. Sorry. The full set usually is called the spectrum. But you have to be very careful when you use the notion spectrum, because sometimes it's larger than n by A, but here it would be n upon log n, okay? Sometimes it is relative. I mean, be a bit careful. When you see the word spectrum, look at the definition. And a point inside, I call that a cusp. Because when you draw, you do a drawing of your function is very flat, modulus is very flat, and okay. They are extremely sharp, so that's why I give this name cusp. So it's a collection of arc, and of course, essentially, they are spaced by 1 by n. I mean, essentially, the function doesn't vary much in little o of 1 by n. So what you want is, we want to bound the number, the size of 1 by n well-spaced subset of C of A. I'm not going to go fully into that. Now I'm going to look at the Starry points. So I'm skipping some part, but if you do some computation and you draw things, you discover that in fact, whatever the interval, it's always the Starry points that give you a cusp like that. So finally, I wanted to prove that at least many Starry points were cusps. And so here is what is the number of Q less than A and A of Q less of A by Q with Q less than A and A prime to Q. This one is about 6 by pi square, 3 by pi square. Maybe 3 by pi square. Yeah. I mean, it's equivalent to that. Yeah, okay. It's 1/2 of 6 by pi square. So you have about A square points A by Q with a small point. And the theorem I'm going to propose the set of A by Q, Q less than A, and S of A by Q is larger than S of 0 by A. This cardinality is larger than, I forgot, there's a constant, I forgot, A square upon log A. Okay. So you see, I'm not able to prove that I have a positive density, but I have to tell you that it's an interesting theorem. I mean, some theorems are less interesting than. So I'm doing some advertisements. So because what do you know? what you know is always the same thing, okay? Is that the sum for S of A by Q square is larger than mu square Q upon phi of Q, S of 0 square. If you had the condition Q square free, you modify the constant, but you still have an asymptotic. Yeah, sure. Okay, so from that, you deduce that there exists A naught mod Q, the biggest, up, such that S A naught by Q is larger than mu square Q upon phi of Q, S of 0. Huh? Phi of Q is essentially of the size Q. I could count this one with phi of Q less than A. It's equivalent to something, I don't know the constant, but there's a positive constant. It works. And I could add mu square Q equal to 1. It is still equivalent to something like that. It's been done by Erdős in 70. Anyway, so for every Q, I'm able to produce 1 point, which is large. Yeah? This one is larger than A. Okay? So the number of Q here is about A. Or I say I have A squared by log A. So where do I find the other point? That's the interesting part of the argument, which is better than this one. So first, you notice that this one was true also. Okay? It gives you the same. That's life. Okay? But then you have an argument. Okay? You have okay, I'm going to state a theorem, and that's going to be the end of this talk. If I can find it, it would be better. If I could find it. That's not that, this one. Yes. So I have a theorem here. Let X inside R by Z delta well spaced. You know, that was the same stuff that I had in the Large inequality. The minimum of X minus X prime inside X is larger than delta. That's delta well spaced. Let Y get UP. Oh, no use. Then we sum upon X, capital X, of my trigonometric polynomial, S of X square, is less than a constant that you forget, and plus delta minus 1 upon log n, log x, cardinality of x, 2, otherwise it's 0, times S of 0. So that's a sharper inequality we can have for the primes. So with respect to the large sieve inequality, that sieve inequality will tell you this one, n plus delta minus 1, and this one is the L2 norm, which is the same as S of 0 here, okay? What you save is that you save log x. What you lose is the log of the size, okay? Green and Tao prove something like that with x to the epsilon, and I prove something like that with log x, and log x is optimal. A consequence of that, the set of X the set of if X is 1 by n well spaced, and for every X in X, S of X is larger than S of 0 by A. See what you get. You get S of 0 square divided by A square. I'm sorry, I forgot a hypothesis consequence. If S of 0 is larger than n upon k log n. I should have put that here. In this theorem. Because if it's an interval where you have no points, so you need many points. Of k log n, and this one depends on k. Okay, so if you have S of x which is large here, you have S of x, S of naught square divided by A square. This S of naught square cancels out with the n by delta and this one. What remains is the cardinality divided by log of the cardinality less than 1, less than A square, because you divide by square. So it gives you that the cardinality is less than, then the cardinality of X is less than some constant, depending on K, of A square log A. You cannot have too many large points. Okay, so now you have two arguments. You know that you cannot have too many large points. You know that you have at least one large point. But look at that. When I set the argument, this one gives me 1 point. If there's only 1 point which is larger, and all the other ones are... Oh, there's no phi of q. Sorry. When you remove the squares, there's no phi of q. If there's only 1 point which is large, and if all the other ones are small, the point which is large has to be as large as S of naught. Okay? But you know that there cannot be so many points that are that large. So maybe it's okay for Q and Q1 or Q2, but for Q3, no. So you have all these inequalities that bound your, and you have an upper bound on the other side, and you see that finally you're forced to have A square upon log A. Then you do all kind of computation to show that it's correct. Professor Balasubramanian showed me a counterexample showing that somehow I cannot remove the log A from my proof. Okay. I agree. Still, we get the feeling that at some point you could have a lot of values that are very small. So there are all the values of SA by Q are of size S naught divided by A0. But then this number of cases like that is small. Okay. So my guess is that knowing the structure of the set S, number of points, you can get that the number of cusps is a small set plus A by Q, plus a Faraday point. That's all I wanted to tell you. I wanted also to tell you that because it's open, you know, removing this log A or finding a counter example, an example of primes where you have this log A. I'm just going to add one. Yes.
The range of Q is the lower bound to have bigger than SR, S0 by A2. That's it.
No, I have a much more general result than this one. Just to simplify that, I put this one. In fact, what you find is that if you have a value which is large, xi, then you have many xi plus a by q. But so you would like to talk about orbits, yeah? But the difficulty is that since it's a finite set, if I want to take the largest point xi plus a by q with q less than q1, maybe it's with a q which is very large. And if I take it as a new xi, xi plus a by q is of size of denominator q square. I mean, you don't have the group structure on this. And so I'm stuck with the combinatoric. It's, I'm just, I promise when I say that it's the last result, I promise it's the last result. I can show that this one does not happen often because I was stubborn and I wanted not to be completely wrong. So what I can prove is that okay, the integral of 1 to a of d, well, dA upon a square, dA is larger than a. So dA is the cardinality of the largest set, okay? If it was a upon a square upon log a, this one would be a upon log a. But we know that it's larger than a. So it cannot happen very often. On the other side, an even weaker result, d of a divided by a cube, yes, dA. So if it was, you know that dA is between a square log a. Okay. And dA is the max of the subset X inside my set of cusps. And X is 1 by n spaced. Yeah? You have your set of cusps, which is a collection of arcs. N is the length of my interval. Yeah? So it's a collection of arcs. Essentially, the function doesn't vary in an arc of length 1 by n. So I take a biggest collection of points. But C of A is infinite, so I have to find a finite number. So that's my D of A. My D of A, according to this theorem, is less than a square log a. And it's larger by this other one, by a square upon log a. I've taken X inside the Fourier sequence, sorry. Because usually I don't, here I restrict to Fourier sequence, okay. And this one is less than, so if it were a square log a, this one would be log square a, and we know that it is less than log a. If it were a square, it would be log a. If it were a square, it would be a. But when you divide by a cube, you dampen the quality of the result quite a bit. But it says that, okay, that's an open problem, and that's the end of my series of lectures. I'm sorry, or maybe you're happy. But anyway, that's the end of this series of lectures. Thank you.
Good. If not, let's thank Professor Ramanujan for having taken time to come all the way and having some difficulty while coming over the flights and having some difficulties while going, the flights being cancelled and he has to advance his trip back and so on and so forth. And yeah, still having taken all the trouble into account. Thank you very much.
Thank you. No, they canceled my ticket when I was coming back. I had to buy another ticket. And yesterday they canceled my return. Okay, there's 15 minutes before problem session or solution session. Jean-Marc has a solution. I don't know. Oh, yeah, we can do it now. Yes, yes, yes.